Welcome to the Fiber Laser Practitioner. I'm Jim Dean, founder and CEO of GW Laser Tech. This is a technical conversation. I've spent over 20 years in fiber laser physics. My doctor is in natural engineering from Penn State, and I've been building fiber lasers commercially since 2005. The reason I'm doing this podcast is very simple. I talk to process engineers all the time who are troubleshooting copper welding issues. And in most cases, they are treating symptoms without understanding the underlying physics. And when you don't understand the physics, you are essentially guessing. So today's episode is about one specific topic, copper welding physics, and specifically why the first 200 milliseconds of every copper weld determine whether the rest of the weld succeeds or fails. Once you understand what's happening in those 200 milliseconds, a lot of things that seemed mysterious about copper welding start to make perfect sense. Let's start with phase 1, which runs from roughly 0 to 50 milliseconds. I call this the reflectivity wall, and the name tells you exactly what's happening. When your laser fires, the beam hits solid copper at room temperature, and the solid copper at room temperature is, for all practical purposes, a mirror for 1 micron laser. It reflects approximately 95% of the incident energy back to the way it came. Your laser is firing at full power, or whatever power you commanded. The material is refusing to cooperate. Almost all of that energy is going right back up the delivery fiber, right back toward your laser source. Now, to break through this reflectivity wall, you need to raise the surface temperature fast enough that thermal conduction doesn't drain the energy before you can reach the boiling point. Copper conducts heat so efficiently that if your energy density isn't high enough, the heat just spreads naturally, and you will never build up enough local temperature to initiate a keyhole. You are just warming a large area rather than piercing a small point, and that's the direct function of power density, not total power, but power per unit area at the focal spot. This is why beam quality is not a marketing specification. Let me say that again, because I heard people dismiss BPP as a spec sheet number. Beam quality is a physics requirement for even initiate copper welding. The power density you can achieve is determined by how tightly you can focus the beam, which is directly determined by your beam parameter product, your BPP. During phase 1, while your surface absorptivity is still at 5%, 95% of your laser energy is being reflected back, and that reflected light doesn't just scatter into the room. Much of it couples right back into the delivery fiber, travels backward to the energy source, back into the signal combiner, backward toward the pump diode, and the pump diodes are expensive, delicate component. If the back reflected power is high enough and it persists long enough, you can damage or destroy your pump diodes. Let's make sure this lands clearly. This happens at every single weld. Every time you fire a laser at copper, phase 1 exists. Phase 1 means high back fraction. This isn't a failure mode, it's a fundamental characteristic of the process. The question is whether your laser system is designed to handle it. This is why back fraction protection mechanism, what we call active back fraction protection at GW. Though some other manufacturers have their own implementations, are not optional on a system doing copper welding. They are mandatory. Without protection, you are rolling the dice on systems, diode lifetime every time you trigger the laser. And because back fraction peaks during phase 1, the laser is most vulnerable in those first milliseconds. At the moment it fires, not during the steady state weld. At the moment it fires. If you are running copper welding and your system doesn't have active back reflection protection, that's the first thing I'd fix before anything else. Once the surface temperature reaches copper's boiling point locally, vapor pressure builds and blows open the keyhole. And when that keyhole opens, absorptivity reflectivity jumps from 5% to around 60%, almost instantaneously. 12 times more energy is now coupling into the material. Welcome to phase 2, the transition. And this is where most copper welding defects are actually born. Think about what's happening physically. The melt pore has been forming under no absorptivity condition. Then, in a span of a few milliseconds, the energy input multiplies by 12. The melt pore that just reached a semi-stable equilibrium now have 12 more power driving it. The keyhole that just opened is trying to stabilize against the vapor pressure from below and the surface tension from the surrounding melt. And it can't do that instantaneously. It oscillates. Keyhole oscillation in phase 2 happens at a frequency typically in the range of 1 to 5 kilohertz. And every time that keyhole collapses and reopens, you have two potential defects. First, spatter. When the keyhole collapses, the vapor trapped inside expands explosively as it escapes. That expansion ejects molten material from the surface, and that's your spatter event. The spatter you see in copper welding isn't random. It's the acoustic signature of keyhole collapse. Second, porosity. If the keyhole collapses and the melt pore solidifies before the trapped gas bubble can escape, the bubble becomes a pore inside the weld bead. In battery welding, where you need electrical conductivity through the joint, porosity is a serious defect. It increases resistance, creates hotspots under load, and in extreme cases can cause joint failure. So what do you do about phase 2? The standard mitigation is power ramping. Instead of firing at full commanded power from time 0, you start at low power, typically 30 to 50% of the target, and ramp up to full power over a window of 10 to 20 milliseconds. The idea is to give the melt pore time to stabilize at each energy level before pushing it higher. You are approaching the keyhole transition gradually rather than slamming right into it. Here is the analog I use. Imagine you are running the water through a pipe at high pressure, and you have a valve that's initially closed. If you slam open the valve fully, instantly, you get a pressure surge, turbulence, vibration, potential damage. But if you open it gradually, over 2 or 3 seconds, the flow stabilizes progressively and you reach the same final flow rate without the turbulence. The physics of keyhole opening is similar. The gradual approach gives you the system time to stabilize at each intermediate condition. Now, here is the catch that not everyone knows about. To execute a proper power ramp over a 10 millisecond window, you need a laser with at least 10 kilohertz modulation bandwidth. If your laser source can only modulate at say 1 kilohertz, which is the case for some older or low-cost systems, you literally cannot ramp fast enough to shape the phase 2 transition properly. The ramp takes too long, and by the time you reach full power, the melt pore has already gone through the unstable transition on its own. This is one of those cases where a specification that looks like a performance number is actually a physics requirement. 10 kilohertz minimum modulation bandwidth isn't about pulse shaping for operation work. It's about whether you can control phase 2 transition in copper welding. If your system doesn't have it, you are leaving process control on the table. After about 150 to 200 milliseconds in a well-designed process, the keyhole reaches what I'd call a steady-state regime. The oscillation amplitude decreases, spatter rate drops, penetration depth stabilizes. The melt pore is no longer trying to adapt to rapid energy change. It's operating at quasi-equilibrium condition. I say quasi-equilibrium deliberately because the keyhole is never perfectly stable. It continues to oscillate, just at lower amplitude, and any perturbation, surface contamination, a small gap variation between the parts, slight beam drift can re-excite the instability and push you back toward phase 2 dynamics. Phase 3 is stable, but it is not unconditional. Let me talk about what matters most in phase 3. First, power stability. In a steady-state keyhole, penetration depth is roughly proportional to power, which means a 5% power variation translates directly to approximately 5% penetration depth variation. On a thicker structural weld, that might be acceptable, but on a, let's say, 0.3 millimeter EV battery tab, 5% of 0.3 millimeter is about 15 micron. That's the difference between full penetration through the tab and a cold lab. A weld that looks fine on the surface but has almost no mechanical or electrical collection below. The battery passes visual inspection. It fails under vibration load or charging cycles. This is why power stability specification on laser source matter for copper welding. We specifically we specify less than plus or minus 1.5% power fluctuation per hour on our single mode product. That's not arbitrary. It's calculated backward from the penetration tolerance on a typical EV battery joint. Over a full production shift, the stability matters more than it does in short-term R&D runs. Second, the ring beam effect. Our F-arm laser, flexible ring mode product, put an annual beam around the central single mode core. The ring beam does several things. But in phase 3, the most important is this. It widens the effective keyhole geometry at the exit channel. The keyhole is essentially a vapor-filled hole in the melt pool. The narrower the hole is at the surface, the faster it can collapse and traps gas bubble. The ring beam keeps the exit channel wider, which means bubble have more time and more space to escape before the pool solidifies. The stable regime expands. Porosity rate drops. You can confirm this quantitatively. For the same weld joint, F-arm consistently produce lower porosity counts than a single mode beam alone at comparable power levels. Third, the thermal accumulation. This one catches a lot of engineers off guard. The very first weld on cold fixture runs differently from 500th weld on a fixture that's been absorbing heat for 2 hours. But a weld reaches phase 3 steady state. But the temperature boundary conditions at the start is completely different. On the cold fixture, the copper part is at room temperature, and the thermal conduction is drawing heat away aggressively during phase 1. On the warm fixture, the bulk part is already elevated, maybe 80 or 100 degrees Celsius, and the condition is less aggressive. You reach keyhole initiation faster at lower power density with a slightly different melt pool geometry. The practical consequence is this. If you develop your welding parameters on cold samples in the morning and then run production in the afternoon, you may see a drift in weld quality that looks like the process instability, but is actually thermal drift. The fix is either to characterize the process across the full thermal range of the fixture, or to implement an active monitoring system that can detect the shift and adjust. I'd genuinely like you to hear from you. If you are working through a copper weld challenge and you are not sure which phase it's in, reach out to us. Drop a comment whenever you are listening to this. You can also find us at gwlaser.tech. Thanks for listening. I'll see you next time.